Okay, let's start. So in the last class we discussed about the vector norm, especially L. So in general it is called LP norm, where P can be 1, 2, all the way up to infinity. And I mentioned that P can be any real number rather than just the integer or the natural number. But if P is less than 1, and then this norm doesn't satisfy this triangle inequality, and thus I don't have a detailed or rigorous explanation, but when using this LP norm in our machine learning objective function, and then as a regularizer. So this LP norm is often used as our regularizer, and widely used form of an LP norm regularizer is when P is 1, 2, and 0, and infinity. And we discussed about the meaning of L0 norm regularizer, which represents the number of non-zero elements in our vector or in our parameter vector. And in the case of an L infinity norm, then it represents the max value. Okay. And there is a more advanced norm, such as this, a vector norm, but we define, we additionally take the input of the matrix W, and in that case the LP norm is defined as this. So we given W, X and W, and then we just multiply them, and then it is still a vector. So if W is maybe 3 by 5, and X should be 5-dimensional vector, and then it will produce the 3-dimensional vector, right? And then we just compute the L2 norm on this vector. Okay. So this is a simple proof that this in the case of an L1 norm, it satisfies all the conditions to be a metric or the norm. Okay, and then the next norm that we will discuss is this matrix norm. Okay, matrix norm. So in the previous case, including LP norm and also this some more advanced type of norm, it is still computes the norm of a given vector. So input should be a vector, right? And in this case, we consider the input as a matrix instead of a vector, and then we consider the matrix norm. And then there could be many different matrix norms, and here in this slide it is saying induced matrix norm. So what does that mean by this induced norm? So it is like, we want to compute the matrix norm, but we actually apply some vector norm concept into when computing the norm of a matrix. Okay, so that way we kind of induced, or we applied, or we inspired from the vector norm to compute the matrix norm. So let's look at the definition over here. So so of course we are given the matrix A, which is a rectangular matrix, and then we take additional two numbers like LP, the P value in LP norm, but this is a two-dimensional vector, and so we take the two different numbers of in the place of P value, so M and N, and then let's look at this. Okay, so let's just simplify this case, and let's say M and N is equal to 2. So in this case, it is computed in this form. So yeah, and then let's also simplify that A is maybe 2 by 2 matrix, which is like a square matrix, and also just 2 by 2 matrix, which is easy to visualize for the two-dimensional vectors. Okay, so in this case, let's suppose, yeah, we are given an additional vector x in addition to original matrix A, of which we want to compute the norm. Okay, and then in this case we introduce additional kind of vector, and then in the denominator, we compute this ratio between them, and then the denominator is the L2 norm of a input vector x, and then the numerator is 8 times the vector norm of an A times x. Okay, so it's like the ratio between the two vector lengths. So we initially are given the vector x, and then we transform it using the matrix A, and then we will obtain the resulting vector as A times x, and then we can consider there are the lengths between the input and output vectors, and then we take the ratio between them. Okay, and that way, yeah, we can understand this ratio. But this x is like additionally introduced vector, right? So we want to compute the matrix norm. So there is there exists no additional vectors in the beginning. So in this definition, so we consider any arbitrary vector x, and we want to choose, okay, we want to choose that vector x such that the ratio between them is maximized. Okay, so depending on different vector x, and then for a fixed input matrix x, input matrix A, and then for a different input vector x, and then the relative ratio between the original input vector lengths and the output vector lengths, right? The ratio could vary, but we want to choose the one particular vector that actually maximizes this ratio. Okay, so that is the notion. And then it is further simplified in this form, where we just we impose additional constraint that instead of just picking up any arbitrary vector, we actually constrain our vector of our selection so that their vector length becomes 1, and then the denominator will always be 1. Okay, so so it is not using any kind of generality. So in this case, if we chose the vector x whose length is 2, and then it will be 2, and then we can just normalize this vector, right? And then if we take the ratio between this guy and this guy, and then the ratio will be the same, right? So it is not losing any kind of generality kind of thing. So we can safely rewrite this left hand side into the right hand side. Okay, so that means we basically choose any vector that has the length of 1 in terms of this 2 norm. Okay, and then what does that mean? We are picking up a particular vector on this circumference of this unit circle. Okay, and then it could be this vector or this vector, and so on. And then for any given vector from this circle, and then we just transform it via this ax. And then, for example, this vector, suppose that vector was transformed into this vector, and maybe this vector is maybe this vector, and then all the lengths of an input vector is 1, and then if we just use all the possible vectors along this circle, and then their kind of trajectory in this ax form, and then it will form this ellipse, and then from here we can see that the vector length is maximized at this axis, or in this vector, right? So the maximum possible ratio between this input and output vector before and after, like transforming this vector through our matrix A, and that is called the matrix norm. Okay, and especially is so vector norm induced matrix norm, because we actually consider the matrix norm by additionally introducing a vector. Okay, and so there are many different matrix norms by using different m and m values, and in this case, when using the matrix, induced matrix norm for this value of 1, and then that means m and n is set as 1. Okay, and then what does that mean? So in this case, we are considering L2 norm, the vector length in the sense of an L2 norm. But when using L1 norm, what is the unit circle that has the unit length in terms of an L1 norm? So in that case, our unit circle, it is not actually a circle, because the vectors, all the vectors that has the L1 norm as 1 will be on this square, right? And then we follow these points, and then we transform it through this a times x, and then it may have some shape like this. Okay, then from here we can maybe pick up some of the largest L1 norm. But here in this case, this guy may not be the largest L1 norm vector, because in the case of an L1 norm, we should compute the L1 norm, for example, of this vector. This length is L2 norm, and L1 norm is sometimes called the Manhattan distance. So in order to move from this position to this position, we cannot go directly to this optimal direction, because there are many buildings, right, in Manhattan, right? So we need to go to this, right? Go to this direction, and so it is the sum of these two absolute value of the coordinates, right? So this is that way it is called the Manhattan distance. And also we can have many choices when we imagine many buildings like this, and then so we go this direction and this direction and so on. But wherever we turn right or up, the sum of these vector lengths will be the same, right? So as a simple case, we just consider this as a L1 norm. Okay, and then you can actually study on your own. To understand the first two relationship. What if we use a L1 norm or an L infinity norm for our matrix induced norm? Okay, so in this case, we know that this constraint can be written as this form: x1 squared and x2 squared is equal to 1, right? But in the case of an L1 norm, we know that constraint is represented as this, right? So we are kind of distributing the total sum of 1 into two vector elements, right? Okay. So let's do it this. Let's just first understand this, okay, as an example. So suppose A is maybe 5 by 2, okay? So in this case, so we have x1 and x2, right? And then in the case of an L1 norm, okay, so we want to distribute the total sum of 1 between these two values, right? And then we know that the resulting vector is a linear combination of these two, right? Okay, and then although I'm not going to give a rigorous proof, but suppose the L1 norm of this vector. So for example, 1, 3, negative 2, and 2, 2, 0, and negative 5. And then what is the L2 norm of this three-dimensional vector over the first column? It is 6, and this guy is 7, right? Because it's I mean, I'm talking about the L1 norm of each column in our matrix, right? So it's an absolute sum of these elements, right? And so we basically compute the linear combinations of these two, and then it's like we have over here and over here. So suppose this guy is 1, 3, negative 2, and this guy is 2, 0, negative 5. So in this case, what will be the linear combination of these two when their sum of weights is equal to 1? It will be, yeah, the line segment between these two. Does it make sense? Because what is the weight corresponding to this vector? So suppose this one is x1 and x2, and then the corresponding linear combination vector is 1, 0, and this guy is 0, 1, because yeah, that is just a single vector. And then what about this point where they have a equidistant from these 2 points? Okay, how can we represent this vector? It will be like 0.5 x1 plus, so this x1 and x2 is not a coefficient, right? So let's call it, so let's call this as a1 and a2, and then this guy is a1 and a2, okay? And then this point will be just 0.5 times a1 and 0.5 and a2, right? So when it is like 0.7 and 0.3, and then it will be somewhere around here and maybe here, and thus all the possible convex combination or linear combinations where the weight sum is equal to 1, and then it will be just a line segment between the two extreme point or two given points, right? So in this case, from here, let's consider their L1 norm, okay? When will this L1 norm of the resulting vector be maximum? Okay, so for this vector, what is the L1 norm? So it is the sum of these two line segments, and for this guy, it will be like this, and maybe like this, or like this, right? And then which one will have the maximum L1 norm? This guy, x1, right? So although it is not a rigorous proof, but we can kind of intuitively understand that the best strategy to obtain the maximum L1 norm vector is to assign all the weights to the column that has the largest L1 norm. Okay. So when computing or considering their L1 norm, the first column is 6 as an L1 norm, and the second one is 7, and thus the corresponding, the best weight that we can obtain the maximum L1 norm will be like assigning 0 and 1, like in this case, and thus overall, if we generalize it, and then it can be represented in this form. So this Aij is each element at i's row and j's column in our matrix A, right? And then for a fixed j, it is like for a fixed column, right? And then summing up over all the i's, and then it will be the absolute sum of the elements of a particular column. And then we are picking up the maximum column over here, right? That has the maximum L1 norm, or absolute sum of the elements of a column. Similarly, you can do the same thing on this L infinity norm. Okay, L infinity norm. So in the case of an L infinity norm, we can actually write the constraint of this into, x1 to be 0 to maybe 1, and x2 also be ranging between 0 to 1, right? So in that way, the L infinity norm is the same thing as the max operator, right? So that way, so this constraint is like this. So it's like, yeah, we freely assign those linear combination coefficient for each, for each of these columns, right? Then, yeah, let's look at this. How can we obtain this maximum? How can we prove that this matrix norm of this A infinity is the same as maximum row sum? Okay, so if you imagine it, and then we can just assign the weights on x1 and x2 freely from the ranges between 0 and 1, right? And then what about the resulting resulting vector? It will be like, let's think of the extreme case. The extreme case will be like assigning 1 and 1. So in this case, it's like 3, right? Yeah, so here one thing that I forgot to mention is that, so more exactly, the L infinity norm is max of, the maximum element value in our vector, but it can be in this form. Okay, so we basically consider the maximum value because, for example, 1 and -2, what would be the infinity norm? 1 infinity and -2 infinity, and then 1 over infinity, right? So this one, does not only diverge, but also it's actually oscillating between negative and positive and so on, right? So, and then we apply this, but if we imagine this one was odd number, I'm not sure exactly, so, but we just define it as the positive value, as this L infinity norm. Okay, so let's take it as just granted without much justification. And also, so norm should be always greater than or equal to 0, right? So it can never be negative number, right? So okay, so in this case, if the vector L infinity norm of a vector is 1, and then this is not actually true, in order to make it true, those two values should be -1, right? Right. So you guys know that the unit circle or the unit norm trajectory, or the set of vectors that has a unit norm will be this guy, right? And then so in the case of an L2 norm, the unit norm vector set is actually the circle, and in the case of an L1 norm, it has like this, and then maybe maybe 100 norm, it is something like this, right? So it actually pushes this line to the to each corner, right? And then what if we use a p as a negative, 0.5, and then this unit circle is actually becoming concave like this. Okay, so we can understand this unit kind of circle kind of thing, depending on different p values of in an LP norm. So so that way, in the case of an L infinity norm, then we can understand the range between these two. Okay, and then let's imagine we just carefully tune or change our linear combination coefficient assigned to each of our columns. So in this case, the resulting linear combination of these two vectors, and then considering L infinity norm, and then L infinity norm will just pick up the maximum absolute value in the resulting linear combination vector, right? And then what will be our strategy? Okay, so we can, at an extreme case, we can assign the weight at each of these values, or each column, as -1 or 1. Or it could be 0 or 0.7 and 0.4 and so on. But in an extreme case, so that we can kind of maximize some value, and then it might be like a best strategy to choose the extreme value, right? And so let's think of like assigning -1 or 1 for each column, right? And then we can actually have an opportunity to change the signs of these two values, right? When multiplying with the -1, and then we can flip the value, or flip the sign of that corresponding value, right? And then we will sum them up, right? And then in the resulting vector, we will pick up the maximum absolute value among them. And then we look at each row and then consider the maximum sum of absolute value. I mean absolute values in each row, right? And then we pick up or focus on that row, and then we just flip the sign if it is a negative value, so that they actually contribute as the positive value, right? So does it make sense? So that way, this guy is like maximum row sum. So in this particular example, let's consider the strategy of maximizing the L infinity norm, and then when considering the last column, it has the maximum value of this absolute sum, right? And so what will be our strategy? So we multiply -1 and -1 to make that resulting value as 7, right? So that will be our max value in the resulting vector, right? And then what if we have maybe this sign, and then the corresponding linear combination coefficient will be like multiplying by 1 and -1, to make their sum to be all positive, right? So still, we can make 7. Any questions about it? Okay, then let's look at this guy. L2 induced norm, or the matrix induced matrix norm when P is 2. Okay. So in this case, it is it is giving us, what is this guy? What's the meaning of it? It represents the eigenvalue of this given matrix. Okay, so we consider the eigenvalue of A transpose A, and then pick up the maximum, largest eigenvalue, and then take the square root of it, and that will be the norm of L2 norm induced matrix norm. Okay, so that is coming from our main topic, hopefully today, of this eigen decomposition and also singular value decomposition. Okay, so it is like if you studied this eigen decomposition from the perspective of a matrix transformation, of like changing the coordinates or change of variables, and then do the scalar multiples, and then send the coordinates back to the original ones, and so that is related to this. So we will discuss and should be able to understand this clearly at the end of our class. And so this guy is equivalently represented, or that is the same as singular value. So So singular value is usually represented as this sigma and sigma max of A. Okay, so that is the same thing. Okay, so let's visit again this slide to make sure we understood this part at the end of our class. But for now, it is okay even if you don't understand this. Any questions about this? And lastly, this Frobenius norm is also widely used norm. So this is not a induced matrix norm. It is just a this is just an direct extension of L2 norm, and also Frobenius norm is actually widely used. So for example, in the case of 1, 2, 3, 4, 5, 6, and then considering their Frobenius norm, and then it is like it is actually the same as like just a reshaped vector version of this matrix. So for example, 1, 3, 5, 2, 4, 6. Okay, then we consider L2 norm of this vector. So in other words, we just take the square of them and then sum them up and then take the square root of it. Okay, so that is called the Frobenius norm. There are many properties on this matrix norms, but in the interest of time, so I will skip this part. Okay, any question before finishing this class? Finishing this lecture. Okay, and then next chapter is about, I believe, singular value decomposition, right? Then so to study this singular value decomposition concretely, I uploaded another lecture material, right? Then let's briefly start with this eigen decomposition. So does anyone is there anyone who doesn't know eigen decomposition at all? So it's part of the curriculum usually in the undergrad level linear algebra. So I think most of you have heard at least and studied about this eigen decomposition, right? And then what's the intuitive meaning of this eigenvector and eigenvalue? Okay. So first of all, eigen decomposition or eigenvalue and eigenvector is only considered for the square matrix, not for rectangular matrix, right? Again, eigen decomposition is defined only on square matrix. And also now, but on the other hand, like the singular value decomposition is defined for any given matrix, okay, for rectangular matrix, and also square matrix, we can obtain singular value decomposition. And also at a high level, singular value decomposition always exists for any given matrix. Okay, for any matrix, we can always define or compute or obtain the singular value decomposition. But in the case of an eigen decomposition, even if we are given a square matrix, not all the square matrix have the eigen decomposition. So there are additional conditions to satisfy for a given square matrix so that it has an eigen decomposition. Okay. So at a high level also, if our matrix A is maybe 3 by 3 matrix, which is a square matrix, so we start with this eigen decomposition, and then in this case, usually eigenvalue and eigenvector is just paired, right? And that pair should satisfy this, right? So if A is 3 by 3, and then we consider some vector x. So this is given matrix A, and then we have lambda and x. Okay, so so this is not an equation that is true all the time with respect to x. So it is an equation where a particular x and also lambda should be found in order to satisfy this. So not all the x vector can satisfy this. So given the matrix A, for example, 1, 2, 3, 4, 5, 6, and 7, 8, maybe 10, and then given this matrix, we need to find a particular pair of this vector x and also lambda. Okay, and then yeah, that is the eigenvector and value pair. And then the intuitive meaning of it is that, so we are given a vector on the left hand side. We're multiplying it with the matrix A, right? And then in general, yeah, the resulting vector will be also the same dimensional vector, because the matrix A is a square matrix, right? And then usually, yes, suppose we are given 1, 2, and 3, 4, 5, 6. And then what is the result? It will be 11, 17, right? And so let's consider the vector magnitude and the direction. Okay, so this vector is somewhere around here, and this vector is maybe it's somewhere around here, right? And so the vector length change it, and also the direction also change it, right? So in general, if we multiply the matrix A, and then the resulting vector will have a different length and different direction. But in the case of an eigenvector, even after multiplied with the matrix A, the resulting vector should have the same direction as the original vector. So that's why we can represent it as the scalar multiple of the original vector. Okay, so that's the intuitive meaning of this, the requirement to satisfy in the case of an eigenvector and eigenvalue. So in this case, if we are given 1 and 1, and then yeah, we can easily verify that it's true, and so it is A times x, the original vector, right? And thus the direction is still the same, only the vector length has changed. Okay, and then yeah, once we obtained a particular eigenvector and the corresponding eigenvalue, and then it can give us much computational savings when multiplying usually the matrix A with some vector, right? So in this case, yeah, how many additions and multiplications are involved when computing this? Okay, so yeah, we have to multiply these two, right? So we need 2 multiplication, and we need to add these 2 numbers. So 2 multiplication and 1 addition. So these are the numbers and the types of an operations needed. And then we have 2 rows, right? So we need this, right? And so so in general, if we are given a m by n, yeah, n by n vector, and then n multiplications, right? And then n minus 1 additions, and n, yeah, times of that, right? So this is the resulting number of multiplications and addition. But in this case, yeah, so it is usually quadratic, right? So it is quadratic in terms of the number of rows or columns, or in terms of an n. But if we compute this, and then it is just a 2 multiplication, right? That's it, right? So at least this can be, yeah, computed, yeah, I mean, in terms of the computational complexity of a linear with respect to the number of dimensions. Okay, so that way, if we are given this, and then if we know that this is an eigenvector, and then it can be represented as this scalar multiple, and then instead of computing this, and then we can compute this more conveniently in a, yeah, with a much reduced yeah, amount of computation. Okay, and then yeah, we given this requirement or equation for this eigenvalue and vector to satisfy, and then we can represent this and x lambda and x, and then we can actually change it into ax minus lambda x, and then ax minus lambda ix, right? And so matrix A, yeah, and then yeah, we can represent a minus lambda I x, right? And so given the original matrix A and the lambda, and we have an identity matrix 1 1 1 0 0 0 0 0 0, right? And then our vector x, right, should give us 0 vector, which is, for example, 3-dimensional 0 vector, right? And so given some matrix where we subtract this part, right, and then we should we need to find some vector for this matrix that where their multiplication should produce 0 vector, right? So here, let me ask one question. So this is our eigenvector that corresponds to this vector x, which can be converted into scalar multiple of the original vector. And then that eigenvector is assumed to be non-zero vector. Okay, so we don't actually consider all 0 vector as our eigenvector, because in case x is a completely 0 vector, and then a times 0 vector will be just a 0 vector regardless of any matrix A. So in that case, it doesn't have any meaning, because as I mentioned, its intuitive meaning is that the direction should be preserved, right, between input and output, but 0 vector doesn't have any direction, right? So we usually exclude, by definition, eigenvector cannot be 0 vector, and thus this vector shouldn't be 0 vector, and the resulting matrix, so this vector, let's say it is B, and then this B times some non-zero vector, and then that should produce 0 vector, and thus it means, like, so we have 3 columns, and then it can be viewed as a linear combination of these 3 columns in the matrix B, right? And then some linear combinations of these 3 columns should be equal to 0 vector. And what does that mean? That means B should have linearly dependent columns, right? And we are talking about the square matrix, so linearly dependent columns means the matrix should not be invariable or singular, right? Okay, so in order to be able to find the non-zero vector x, and then that means we need to make this a minus lambda I as a singular, right? And so, for example, in this case, so let's suppose A is 2 by 2 matrix in this form, and then is matrix A singular, or is it invariable or not? So if we compute the determinant, then 6 minus 30, and so it's non-zero, and so it is invariable, right? But once we subtract lambda I, and then it should be invariable, right? So we need to find such a lambda that makes this B or a minus lambda I non-invariable. So in this case, this guy has the lambda along the diagonal, right? And so it is like minus lambda along the 2 diagonal elements, right? And then it need to be singular, and thus we can we can just set up or build this equation by using the determinant of this matrix. So if it is singular, and then equivalently its determinant should be 0, and thus 2 minus lambda, 3 minus lambda. So this is corresponding to AD, and 5 times 6 should be 0, right? So the root or the solution for this equation to make the determinant as 0, and that is our eigenvalue. And then once we found the solution from this equation, and then suppose one of the solution is 8, right? So if we just plug in 8 in the place of lambda, and then we can see that it's a 0. And we basically have to solve this polynomial equation. It's a second order polynomial equation, right? And so it is easy to find the solution, right? But even if it is a third order or even a higher order polynomials, then we need to find the solution that satisfies that equation. And that is usually found by our computers through some iterative algorithms such as the Newton method and any other methods that finds the root of a given equation. Okay, whether it's a polynomial equation, higher order polynomial equation, or any other types of equations, and then we can kind of approximate some function as like first order Taylor series expansion kind of thing, right? So you guys know how the Newton method works. So it is like this. So and suppose our given function is like this, and then it's basically an iterative process that finds the two solutions. Geometrically, the root of this fx equals 0 is the x value that crosses this x-axis, right? So here, it's so in this case, if we do the Taylor expansion through the first order approximation, and then it's like this, and then we move from this to this point, and then at this point we do once again the Taylor expansion like this, and then it is really far. So in this case it looks like diverging, right? So let's see. Let's start with this point. Then after this Taylor expansion or first order approximation of this given graph, and then we consider its solution, right? And then the solution of this simple line is over here, right? And then this will be our new point in the next iteration, and then from here, then we over here. So it is also diverging. Anyways, so after doing this iteration, and then maybe over here, so from here, and then it will give this point, and then from here it will also give the point closer to one of the roots in our function, right? So this is the rough idea of this Newton method, but I'm not I don't exactly remember how to take care of this diverging case, but roughly the main idea is that we approximate the complex function that we are given as just a first order polynomial as y equals ax plus b, and then finds the solution, okay, and then that will be our next point in our iteration, okay, so back to this equation. Given whatever polynomial or any other complex equations, we have a way to compute, although it is an approximate solution, but we have the algorithm to find the solution through some iterative processes. Okay, so once we obtain the lambda as this value, and then once we plug this, obtain the solution in the place of this a minus lambda I, and then the resulting matrix is over here, and then let's verify it is singular. And then if we multiply AD and minus BC, and then it will be 0. And also intuitively, and what is the meaning of this singular matrix? It means the columns are linearly dependent. At least one columns should be linearly independent. Linearly dependent, right? So yeah, when considering, yeah, suppose we have maybe 4 columns in 4-dimensional space, and then it should be I. So that is corresponding to invertible case, and then if we find the D case, which means this third column is represented as a linear combination of these previous two, and then that's when we have no inverse matrix of this, right? Okay, so in this matrix, so we have these 2 columns, and so so the first one is I, and the second one should be D, right? So yeah, we can easily find the scalar value that is multiplied with the first column to make the second column, right? So -1 will be our linear combination coefficient, and so our solution will be, so this guy is a -1 times this, right? And so like A2 equals -1 times A1, and thus A1 times 1 plus A2 is 0, and thus linear combination coefficient we can obtain easily. The solution, one of the solution will be 1 and 1, right? That would be the linear combination coefficient to make the 0 vector. Okay, and so this guy is what? This guy is satisfying this equation in the place of this vector x, and so that is our eigenvector, right? So this is how we can find the eigenvector, right? And so at a high level, we first subtract lambda from all the diagonal elements, right? And that lambda should be the same value across all the diagonal elements, and then we compute its determinant and set it as 0, and then finds out the set of the solutions of that equations, and for each solution. So in this case, this is a second order equation, and so we should have another root or another solution. So one of them is 8, and then if you take the apply the formula, analytic kind of solution for the second order polynomial or equation, and then we can easily see that another solution is -3, and then we just also plug this in to this representation, and then set it as 0, and then finds out the corresponding vector x, and that will be another eigenvector that corresponds to this eigenvalue, right? So at a high level, we first construct the determinant of a minus lambda I and set it as 0, and then finds the set of all the solution, and for each of our eigenvalues, and then we plug that into this a minus lambda I times x equals 0, and then we find that vector x, and then that will be our eigenvector corresponding to the particular eigenvalue that we used to make this equation. Any questions so far? So this is a kind of review of our eigenvalue and eigenvector. Okay, then and then this diagonalization is a kind of important thing. So there are several different directions to understand this equation, but this time let me describe it in the other way around compared to the flow described in this slide. So let's just construct this A times V, where V is some matrix whose columns are eigen vectors that we found. So in the previous case, we found -3 and 8 as 2 eigenvalues, and this eigenvector is found as -1 and 1, right? And for this eigenvalue, we found another eigenvector over here, right? And then given this original matrix as 2, 6, 5, 3, okay, and then on the right, let's just place each eigenvector that we found as the columns of this matrix. So for example, the first column will be this guy, 1, 1, which is the first eigenvector, and the second eigenvector is found as this 1 and negative 5/6. Okay, so this is matrix A, and let's call this matrix as a V, whose columns are our eigenvector. Okay, and then now we rewrite once again this V, and 1, 1, and 1. Okay, and then we introduce another matrix D, which is a diagonal matrix, and this diagonal diagonal elements in this matrix is our eigenvalue. So for 1 and 1, it is paired with eigenvalue of 8, right? So the first element we populate it as 8, and then for the second one we place it as eigenvalue in the second diagonal element. Okay, so it's V times D, and yeah, this AV is equal to VD. And let's look at why. Okay, so again, we apply this column combination perspective in order to understand this. Okay, so let's first look at the right hand side, and then we have these two columns, right? And then this guy will work as a linear first set of linear combination coefficient to produce the first column on the left hand side, right? So again, on the right hand side, so we have 8 and 0, right? So that will work as the first set of linear combination coefficient to produce the first column of this resulting matrix, right? And so it can be represented as this 1 and 1 times 8. Okay, and then what about the second column? It is represented as negative 3 times 1 and 5/6, negative 5/6, right? Okay, so this is the resulting matrix, right? So far so good, right? And then now let's look at the left hand side. Okay, the left hand side is, we have the matrix A that has two columns, and also this vector, for example, the first eigenvector V1, okay, and then it will work as the linear combination coefficient, but more importantly, at a high level, what will be the first column of the resulting matrix of A, V, and then the first column will be A and V1, right? Because V1 will work as the first set of the linear combination coefficient that will produce the first column. And then we have V2, and the same columns are used as our common basis vectors, right? And then V2 will work as a second set of linear combination coefficients, right? So overall, we can represent it in this form, right? And then this matrix and this matrix should be the same, right? And so this AV1 should be equal to lambda 1 times V1, right? And so by matching these two matrices column by column, so if the two matrices are exactly the same, and then the first column of these two matrices should be the same, and the second column of the two matrices should be the same. So if we just decompose it into multiple equations, column by column, and then the first equation will be A V1 is equal to lambda 1 times V1, right? So that actually gets back to the original definition of our eigenvalue and eigenvector equation, right? So that's the relationship between this multiple equations for each pair of eigenvalue and vector. For AV1 is equal to lambda 1 V1 and AV2 is equal to lambda 2 V2, right? If we found the multiple pairs of an eigenvalue and vectors, and then we can just set up or build these multiple equations, okay? And then the single equation of A times V is equal to V times D. So that is just a single matrix equation form of, that involves all the pairs of an eigenvalue and vectors. Any questions so far? Okay, and then what is eigen decomposition? Okay, so so in general, suppose we are given 3 by 3 matrices, and in practice, so in this case, if we just restrict ourselves within the real number domains, and then the determinant of a minus lambda I will always give us the third order polynomial equations. Okay, so the third order polynomial equations will generally have the 3 different roots, right? But in terms of their whether they are real or complex numbers, sometimes all the 3 values can be real number, or sometimes only one of them is real, and the 2 of them are kind of conjugate, kind of complex numbers, right? If one is 2 plus 3i, and then the other should be 2 minus 3i, or something like that, right? So that way we may have strictly less number of real values than 3. Okay, so in this case, again, we only consider the real numbers as our eigenvalue and also eigenvectors, and also of course the input matrix A should be real, composed of all real values. So in this case, we can find only one pair of an eigenvalue and eigenvector that are real numbers, right? So in that case, what would be the form of this AV and VD? Or in general, suppose we are given n by n matrix, and then maybe it is maybe 5 by 5, and then we only found 3 pairs of real eigenvector and values. So in this case, still, if we align AV and VD, and then form, by just collecting the 3 eigenvectors as V and 3 eigenvalues as like this. So this is lambda 1, lambda 2, lambda 3, right? So once we align this, then we have V over here, the same V, right? And then we have so it is a 5 by 5 matrix. So just to make it more intuitive, so let me just make more dramatic, because it is like only 3 vectors that are in the 5-dimensional space. And then what about our A? A is still a big 5 by 5 matrix. Okay, so here V is composed of all the found eigenvectors, but we only found the 3 vectors in the 5-dimensional space, and thus this V can be, of course, can be rectangular matrix, right? Rectangular matrix. So in this case, this case is when this matrix A has no eigen decomposition. So here we can think of an additional condition that in order to have an eigen decomposition, in conclusion, to have the eigen decomposition, we need to make this matrix V as a square matrix, and in that case, if that square matrix V is also an invertible matrix, okay, square and invertible matrix, and then this AV is equal to VD, and then V should have an inverse, and thus A is equal to VD V inverse, right? So this form is called eigen decomposition. So even when we have a strict yeah, we found a strictly less number of an eigenvector and value pairs compared to the dimension n, where the matrix size of an A is n by n. Okay, so like in this case, it's the original 5 by 5 case, and then we found only 3 pairs of an eigenvector and value pairs. And in that case, V is not even a square matrix, and thus we cannot find the V inverse. But what if we found like 5 different pairs of eigenvalue and vector pairs, and also this in that case at least the V matrix V is a square, right? And also if the columns of V are linearly independent of each other, and then that is when this matrix V is invertible, and then we can write it in this form, right? Okay, so so in conclusion, in order, given a matrix A, if A has an eigen decomposition, and then A should give us n linearly independent eigenvectors. Again, it should give an n eigenvectors to make V as a square matrix, and not only that, we also need all the eigenvectors. N eigenvectors should be linearly independent. Okay. So there is a notion of geometric multiplicity and algebraic multiplicity. So far, we at least understood the requirement for the matrix A to have eigen decomposition, which is having n linearly independent eigenvectors. And what kind of determines that? How can we decide, or how can we determine whether a matrix A has the eigen decomposition or not? And that is related to like geometric multiplicity and algebraic multiplicity. But I think I don't think I have much time to cover that in more detail. But okay, and then let me just quickly finish this eigen decomposition before we move. We are ready to move to singular value decomposition. So suppose our matrix A has eigen decomposition. Okay, and then we can also we can understand this matrix matrix A as a linear transformation matrix. So the situation is that A has eigen decomposition, and now we view this matrix A as the transformer or transforming matrix of a given vector X. Okay, so if A is a 5 by 5, and then it will send 5-dimensional vector into another 5-dimensional vector. Okay, so in this case, let me describe kind of main kind of intuition or idea. So here, the really important concept is this change of basis. Okay, so suppose we are given this 1, 2, 5 as an input vector X, which is used over here, and we consider this A times X. Okay, and then suppose in this 3-dimensional space. So in this case, our matrix A will be 3 by 3, and then suppose it is it has eigen decomposition, and then it means it has 3 linearly independent eigenvectors. And then now we can kind of think of this eigenvectors as a new set of bases that represents this entire space of 3-dimensional space, right? Okay, so it's like this. So let me just make it simpler. So suppose our given vector is a 1, 2, and our eigenvector is So let me follow this example. So our given vector x is 4, 3, and suppose our matrix A has 2 eigenvectors, and that eigenvector is this 3, 1 and negative 2, 1. So in this case, we have 2 eigenvectors, and then externally given input vector x. Okay, and then we want to decompose x in as a linear combination of our eigenvectors. Okay, so again, eigenvectors can work as a new basis vector for any given vector in the same dimensional space, right? Because in n-dimensional space, if we have an n linearly independent vectors, which are our eigenvectors, and then we should be able to represent any given point as a linear combination of these eigenvectors. Okay, so for example, in this case, 4, 3. Okay, so 4, 3 can be represented as this guy. So 3, 1 times 2 and negative 2, 1 times 1. Okay, so that is the linear combination representation of in terms of an eigenvectors, right? And why do we do that? Okay, once we decompose this input vector as a linear combination of eigenvectors, and then we can actually take the advantage of this kind of computational kind of savings. Okay, so here, if we imagine this a times x, okay, and then a times this, right, and then a can be distributed, and a can be over here and over here, right? So far so good. Okay, and then this part and this part can be converted into lambda 1 times 3, 1 and negative 1 and 1 and lambda 2. Okay, then we still have an additional 2 and 1, okay, which was a linear combination coefficient to represent the given input vector as a linear combination of the eigenvectors. Okay, and then how about a to the power of an n times x? So let's imagine this situation where we need to multiply a to the power of an n. Okay, and then it is like n a to the power of an n, a to the power of an n, right? And then it's a squared times a v1 can be represented as this form, a times a v1, and this can be simply simplified as a lambda 1 v1 and a, and this is a scalar, and a can be inserted or moved in between. Okay, and then a times v1, and additionally we have a lambda 1, and thus this guy is represented lambda squared v1, or this should be lambda 1, right? Okay, so I tried to finish this part, but because it took it's been let's take a break first, and then let's resume at 3:30. 네, 일단은 우리가 오늘까지 수업한 것들 네, 여보세요? 아, 예. 아, 혹시 전화하셨는데?
여기 못 뽑는 거 하지 마세요. 근데 약간 이거랑 라포 리더십은 뭐지 비슷한 거 같아요. 그냥 하나의 그 배트가 그냥 없애버리잖아요. 이렇게 같은 거 그냥 안 써버리고 아 근데 지금
네. 한 4시, 한 4시 반 정도를 생각하고 있어요. 저 그거 지금 삭제했거든요. 네, 네, 처리 부탁드리겠습니다. 네, 감사합니다. 네.
제가 200점이고 진짜 될 때마다 하드를 더 근데 미팅 하는 거 공부해서 되게
Okay, let's continue. Okay, so yeah, I think this point is really important, and this is a kind of essence of the matrix and vector or matrix multiplication. So yeah, in general, yeah, we when multiplying a given vector with a particular matrix, and then yeah, this matrix, although it is not revealed at first, because we need to compute the eigenvectors and eigenvalues of a matrix of a given particular matrix. But once we found eigenvalues and eigenvectors, and then for whatever given input vector, and then we represent it as a linear combination of eigenvectors. Okay, and then matrix multiplication with this input vector. Okay, so here, so given a matrix this 4, 3, and then our input matrix is okay. Our input matrix is not given at first, because we assume that we initially are given an eigenvector and value pairs at first. But anyways, we can easily compute their corresponding corresponding matrix that will have this eigenvalue and vectors. But anyways, in general, if this matrix A is multiplied with the arbitrary vector x, and then it will change. It will change the direction and the magnitude, of course, right, in general. And also, like in this case where 1, 2, 3, 4 and 5, 6, and then we have these two resulting elements in our resulting vector, and each of these two values is actually a mixture of these two numbers. I mean, those two elements will be mixed together to generate the first element and second element in this matrix vector multiplication, right? So that way, this matrix vector multiplication will actually mixes together or combines together the values in different dimensions. Okay, because this 5 times 1 and 6 times 2 will produce the first number, and thus this first number is actually a linear combination of the multiple numbers. But in the case of this guy is represented as a linear combination of our eigenvectors, and then suppose our eigenvectors is a 7 and -1. I mean, it's just a hypothetical example, and 6 and 2, for example, and then suppose this guy is represented as maybe 3 and 4. I mean, this is clearly wrong, but let's just assume that this was decomposed it into this form. Okay, and then once we multiply a over here, and then instead of this 5 and 6, we can now consider this vector 5 and 6 as 3 and 4. And what are these 3 and 4s? I mean, these two numbers are the linear combination coefficient corresponding to our eigenvectors, right? And then if we imagine this matrix multiplication with the A, okay, and then this again, this guy will become 3 times lambda 1 and 7 and -1 and 6 times 2 and 4 times lambda 2, right? So 3 and 4, those two numbers actually change it into 3 times lambda 1 and 4 times lambda 2. So if we multiply it with the A once again, and then lambda 1 squared and lambda 2 squared, right? And so in terms of these two coefficients with respect to our eigenvectors, okay, in that case, when multiplying matrix A, and then those two numbers, which are the linear combination coefficient with respect to our eigenvectors, okay, those two numbers doesn't mix up, okay. So when multiplying A, and then A will be just converted into just a individual scalar multiple within each dimension, okay. So that doesn't mix up these two numbers, okay. So that is kind of a point. I'm not sure if it is yeah, it was yeah, it conveyed my meaning intuitively, but yeah. So it's yeah, geometrically we can think of this process in this form. So in general, if we multiply this vector with some matrix, and then this 5 and 5, 6, yeah, will be converted into another vector that has a different length and also different directions. And this vector, if we multiply A once again, and then this vector may jump into another random point. I mean, it is not completely random, but yeah, another vector that has completely different magnitude and the direction, right? But once we decompose this guy with respect to our eigenvector, so for example, in this case, this is our input vector, and then once we decompose it with respect to our eigenvector, I mean, we assume that, so in this example, v1 and v2 are our eigenvectors that we separately obtained or computed by just applying this eigendecomposition algorithm on the given matrix A. Okay, and then this vector x is decomposed into v1 times 2 and v2 times 1. Okay. Okay. So now this one single vector is now decomposed into this guy and this guy, and then once we multiply A, and then it is equivalent to multiplying this A onto this, and also multiplying A onto this, and then we combine them together at the end, right? But at least when multiplying A with this vector doesn't involve, and also this vector direction will stay the same, right? So this vector is decomposed into 2, and once multiplied with the A, and then this vector, the direction stays the same, but only the length will be magnified by our eigenvalue, right? So this direction will stretch or shrink, and this direction will stretch or shrink, but the direction itself will be the same, right? And then at the end, we now combine them together to find out the final result, right? Because originally, we want to multiply A with this vector, and this vector is the addition or the summation between these two. And then for each of them, once multiplying A, then the direction will change. Direction will stay the same. Only the magnitude will change. And then, yeah, after doing that simple kind of computation, we just add them together at the end. That will be the result. I mean, that will be the same result as just multiplying A with this vector. Okay. So this kind of intuition is really, really important. And our matrix multiplication, okay, matrix multiplication, although the matrix multiplication is not a complicated process, but at least, as I mentioned, yeah, we don't know this vector, I mean, where this vector jumps to, right? So it can be kind of a random, arbitrary kind of vector that has a different direction and vector length. But once we apply or understand in this form or in this perspective, and then we can have many kind of interesting insights about this matrix vector multiplication. So, for example, so it is related to power iteration. So suppose we pick up arbitrary vector x, and then we keep multiplying A over and over. Okay, we multiply A over and over, and then the first multiplication will actually stretch it with the amount of an eigenvalue and also its own eigenvalue as well, right? once A multiplying A again, and then it will be further multiplied, right? And so the length will be like, so the eigenvalue, if the eigenvalue was maybe 2, and then it will be 2 to the power of an n. And if the eigenvalue of this guy was, for example, 0.7, and then 0.7 to the power of an n, right? So it is actually reduced. The length is keeps reduced, and then this guy will be increased. And then once we add them up, and then what will be the resulting vector converging to? So once multiplying A over and over, and then the component along this direction will be magnified, or will keep increased, but this direction will keep shrunk, right? And then once add them back at the end, and then the direction will be almost the same as this direction. Okay. So that is the main idea of this power iteration. So I mentioned that, I mean, we briefly understood or studied in about an hour ago about how to compute each of our eigenvalue and eigenvectors. But if we want to find only the largest, I mean, only the eigenvector that has the largest eigenvalue, okay, and then we can just keep we just to choose with any random vector. It can be this vector or that vector and so on, and then it will only make the linear combination coefficient with respect to this fixed eigenvector different, right? It will give a different linear combination coefficient, but once we multiplying A over and over, then it will be magnified a lot larger than the other ones, right? So that way, the resulting vector direction will give you the direction of the eigenvector that has the largest eigenvalue. So that is the power iteration. Any questions? And then I'm gonna skip the detailed formula or derivation, but once you got this insight, and it will be easy to follow. Okay, and then now let's discuss about this singular value decomposition. In the case of this singular value decomposition, I mentioned that this is defined for any size of a matrix, whether it's a square or rectangular, right? And then this is the form. So if we compare it with the eigen decomposition has this form: V and D and V inverse. And what's the size? So suppose A is 3 by 3. And what is the size of V? V is 3 by 3, and D is also 3 by 3, and also 3 by 3. So where is our eigenvector? So these three column vectors are our eigenvalues, and those three values will be those three vectors are eigenvectors, and those green ones are eigenvalues. And this guy is inverse of this guy, right? And in the case of singular value decomposition, let's look at the shape first. So if it is a 5 by 3, okay, and then it will decompose it into these three matrices of 5 by 5 and 5 by 3. So in the middle, it is actually the same size as the input matrix. And also V, which is a 3 by 3. So on the left and the right, so those two will be square matrix. And in the middle, it is almost like a diagonal matrix. So we have the diagonal entry over here, and we have 0 over here, and then also we additionally have all zeros in this non-square part. Okay, so this is the default shape of our eigen decomposition. Singular value decomposition. And in the case of an eigen decomposition, the main requirement is that we need to have 3 linearly independent eigenvectors, right? And even though it is represented as the product of three matrices, but yeah, that last matrix is actually inverse of the first one, right? So we need to obtain this form by just carefully choosing the two matrices of V and D. So these are two opportunities that we can kind of carefully choose in order to obtain this eigendecomposition. But intuitively, in this singular value decomposition, this V inverse is not a it is not kind of a subsequent matrix obtained by the first one. It is its own matrix. So we have U and sigma and V transpose, and U and V transpose can be totally different matrix. Okay, so we have more freedom to obtain this representation or this decomposition out of this input matrix, right? So that way, that is sometimes not possible to obtain, but in this case, because we have much more freedom, we can represent or we can obtain this decomposition all the time. Okay, but still we impose additional kind of constraint. Okay, additional constraint or condition to define our singular value decomposition, which is that the columns of U. So in the place of U, we had originally V in the case of eigendecomposition, and the condition or requirement was that those three vectors are linearly independent, right? But in the case of singular value decomposition, the columns of U. So for example, for here, we have this 5 different columns, and they should not only be linearly independent, but also they actually need to be orthogonal to each other, or in short, this square matrix or 5 by 5 matrix should be also normal matrix. Okay, and so also, I mean, having also normal or orthogonal columns is more strict condition than having linearly independent columns, right? So in other words, if your columns are linearly independent, it is not necessarily be orthogonal, right? Because their angle can be kind of different angles from 90 degrees, right? But if we have orthogonal columns in our matrix, and then it guarantees that these columns are linearly independent, right? Okay, so we impose much strict condition here that our column should be also normal, and also this matrix V, which is giving us another degree of freedom, right? So this is totally different matrix from the first one, but this guy, it also need to have also normal rows in this matrix. Okay. Okay, so U and V transpose should have also normal columns. Okay, so that is our main kind of constraint to obtain this SVD. Okay, and then we understood this AV and VD is actually, in case V is invariable, and then it can be written as our eigendecomposition, right? And so there is a relationship between these two, right? And then understanding this equation, the first equation, column by column, that gives us our original eigenvalue and vector equation, right? AV equals lambda V, right? So that was like a column by column kind of equation, right? Decomposed from that single matrix equation, right? So similarly, this guy can also be represented in like the first form. So we multiply V on the right, and then AV is equal to sigma times, U and sigma and V transpose and V. And again, V is orthogonal matrix, which is square matrix and also having also normal columns. And thus, we know that this guy is identity matrix, right? Okay, so we can cancel this out, and so we obtain AV is equal to U sigma, right? Okay, and then similar to the case where this single matrix equation can be understood column-wise, right? To obtain like column-wise eigenvalue vector equation, and then we can also understand this into, let's see, yeah, maybe it is not written here. Oh yeah, we have it here. Okay, so okay, so previously we obtained AV is equal to sigma, no, U sigma, right? Okay, and then A times V, where V, which was in the place of U sigma V transpose, right? So V transpose, I mean, that matrix V had an orthonormal columns, and so this V will have those columns that are orthonormal, right? And then we multiplied A on the left, and then yeah, it can be represented as, I mean, each columns can be represented as the same matrix multiplication of an A with different linear combination coefficient of V1 and V2 and so on, right? So yeah, how we understand this is exactly the same, right, as in the eigendecomposition case. Okay, and then let's evaluate this U sigma. Okay, suppose U has those columns of U1 through UN which are also normal by definition, right? And then the this let's see, where is it? Okay, yeah, we have sigma over here, and sigma is our diagonal matrix, right? And then we have a diagonal element over here, and so what would be the first column? This guy will work as the first set of linear combination coefficient, and then we only have only one non-zero at the first element, and so yeah, it is multiplied with the first, and so we obtain this scalar multiple of U1 and another scalar multiple with the U2 and so on, right? So again, yeah, once we multiply the diagonal matrix on the right, and then it gives us the scalar multiple of individual columns, right? Okay, so we understood this part, right? And then now we equate, or we obtain column-wise equation, okay? And then column-wise equation is sigma 1 times U1 is equal to this kind, A and V1, right? So we finally obtain this one as the column-wise equation that we need to satisfy in the singular value decomposition. Okay. Okay, and then let's look at the shape. So if A was 5 by 3, and then this U will have 5-dimensional vector, right? And then this V transpose, or this V, will have 3-dimensional vector, right? And so if we look at this, V is 3-dimensional vector, and we have sigma, and it is 5-dimensional vector, right? So if we just imply, or yeah, think of this eigendecomposition equation, and then it is like A V was equal to lambda V, right? So in this case, yeah, I mean, in the case of an eigendecomposition, those two vectors were actually the same, right? And thus we actually had the intuition that, okay, the vector direction doesn't change at all, right? But in this case, those two vectors are living in completely different space. So this is living in 3-dimensional space, and that is a 5-dimensional space, right? So there is no notion of like maintaining the same dimension. Okay. but still, yeah, but still, you can think of given some vectors, okay, there is a special vector in the input domain of the three-dimensional vector, and then this guy is mapped to a particular five-dimensional output vector, and this times a scalar multiple. Okay, so this whole matrix is actually reduced down to a scalar multiple. So we can kind of do the same analogy, where our input vector x, which is our three-dimensional vector, and we first decompose it into into the linear combination of our. So this is called the right singular vectors, and this is called the left singular vectors, because we have an A equal to U sigma V transpose, and the U has five-dimensional vectors, right? And so that is called the left singular vector, and V is the columns of V over there is called the right singular vector. Okay, and also yes, those sigma is called the singular value. Okay, and then we can imagine that the input vector x can be decomposed of a linear combination of right singular vectors, right? And then maybe our arbitrary input vector is maybe 3 times this, and maybe 5 times another right singular vector, and then once multiplying A with this linear combination of right singular vectors, and then we distribute A with each terms, and then matrix multiplication of this A with this right singular vector is actually reduced down to scalar multiple of the corresponding left singular vector. Okay, so that way the overall process is almost the same. Okay, but we are now dealing with two different spaces where we originally have, input is a three-dimensional space and the output is a five-dimensional space, and then now we have also normal right singular vectors. For example, like we have a 3 also normal singular vectors, and then that is corresponding, that is mapped to its own also normal left singular vectors. Okay. So we have 3 also normal vectors in an input domain, and we have 5 also normal vectors. 3, the same number of right singular vectors where each of them is corresponding to the other, right? And this guy is actually converted into this, but the main point is that matrix multiplication is just converted simply into scalar multiple. Okay, and then how can we compute this singular value decomposition, or more exactly, U and sigma and V transpose? And there is no no separate algorithm, specialized for singular value decomposition. The main algorithm to obtain singular value decomposition is just the same as eigen decomposition. And let me show how. So we can think of this A transpose and A transpose A. So if our A was Y by 3 matrix, and then A transpose will be 3 by 5, right? And thus we will have 5 by 5 matrix. Okay, and then we have this square matrix, of course, right? And then now we can think of the possibility of having eigen decomposition of that square matrix, right? So even though we started from the square rectangular matrix, once we compute A transpose, and similarly A transpose A will give us the smaller square matrix of 3 by 3, right? And then we can now consider the eigendecomposition of each matrix. Okay, and here, you guys remember that eigendecomposition can sometimes exist, or sometimes we don't have an eigendecomposition, right? So the condition was, whether we have n linearly independent eigenvectors or not, right? So in that, so even though this eigendecomposition can exist or not for depending on the input square matrix, but for this special form of a square matrix, which is like which is computed as A transpose A or A transpose from some rectangular matrix. Okay, and then we can guarantee that, or we can prove that those two will always have eigendecomposition. Okay, so once we form these two matrices, and then each of them is guaranteed to have, or they always have eigendecomposition. So that is okay, and then let's having that in mind, although we haven't proved it yet, but let's relate this eigendecomposition of this A transpose or A transpose A with its singular value decomposition form. So suppose we already obtained the singular value decomposition of an A, and then it will be represented U sigma V transpose, and then A transpose will be represented as this, right? And then V transpose V, because V has also normal columns, right? And so it is always represented as an identity. And then U sigma transpose and U transpose is our result, right? And then this sigma is diagonal element, right? And so maybe 2 and 3, 0, 0, and 2, 0, 0, 3. What is the result? It is just element-wise squared value, right? So that is the meaning of this sigma squared, and so it is represented as a U and sigma squared, which is still diagonal matrix and U transpose. Okay, so here okay, let's compare this as the singular value decomposition form when considering this as our input square matrix B. Okay, so if B has eigendecomposition, okay, and then it will have some matrix V and D that will satisfy this, becoming A, right? B. And then if we just compare or plug this V in the place of U, in the place of V, we just plug U over here, and this guy is a diagonal matrix, and this guy is placed in the place of it will be put in the place of V inverse, and then those two matrices U and U transpose have the inverse relationship, right? Because U is orthogonal matrix, and thus U transpose will be its inverse, right? And so this representation is automatically obtained over here. But it's like but it's not kind of logically perfect, because we initially assumed that A has a singular value decomposition, which is this U sigma V transpose. But I mentioned that in order to obtain singular value decomposition, we actually obtain eigen decomposition first, and then from there we obtain singular value decomposition. So how we compute this singular value decomposition is we first compute this AA transpose and then perform the eigen decomposition, and then although we haven't proved it yet, it is guaranteed to have a eigen decomposition having this form, right? And then and then in that case, let's assume that let's assume that our eigen decomposition of AA transpose gave the matrix V as V such that the columns of V are not just linearly independent, but they are actually turn out to be orthonormal columns. Okay, and then also this diagonal matrix. Okay, so when it is a little sorry for a little bit a little bit noisy kind of explanation, but in order to derive this singular values from this matrix D, what's the condition for D? So D should have non-negative elements in order to give us the singular values, because here sigma squared is actually the squared value of some singular values, whether they are positive or negative, right? But once squared, they will be positive values, right? And then those will be the eigenvalue when doing the eigen decomposition of the AA transpose, right? So from here, let's suppose we obtained this eigen decomposition of AA transpose, and then let's suppose we obtained U and the square root factor of this sigma, okay, from this D, and then we need the condition that V is not actually, in fact, V is not just having an eigen linearly independent columns, but they are actually giving us also normal columns, okay, and also each eigenvalues contained in our D are all positive values. Okay, in that case, we have no problem of taking the square root of each positive eigenvalues to obtain our singular value in the place of this sigma. And also, if this guy is also orthogonal matrix, and then we can just set this guy is equal to U. Okay, so so far I just explained some scenario that makes this guy give us the solution, right? I mean, I just gave the scenario that makes this kind of conversion possible, right? And in fact, once we do the eigen decomposition on AA transpose, and then it will give us all the positive eigenvalues all the time, and also it is always true that this one will give us also normal eigenvectors. Okay, so that is called the spectral theorem, and also it is called symmetric eigen decomposition. Okay. So let me just give a kind of high-level overview, although we don't have time to look into all the details of this spectral theorem or symmetric eigen decomposition. But this AA transpose, we can at least verify that this matrix AA transpose is symmetric matrix. Okay, it is symmetric. So in other words, suppose 1, 2, 3, 4, 5, 7, for example. And then, so this is A, and A transpose will be 1, 2, 3, 4, 5, 7. So this will be A transpose. And then once you compute it, it will give us 2 by 2 matrix, but also this matrix will be symmetric, which means those two values will be the same, right? So that is the definition of the symmetric matrix. Okay. So, and also it can be proved in the following way. So if we, the symmetric matrix should have, so suppose we are given the matrix B, and B is symmetric, and then B should be equal to B transpose, right? And so given B as this A transpose, and then let's transpose it, and then this transpose operator will just change the order between them. So for example, in general, A, B, C transpose will be C transpose, B transpose, and A transpose, right? And so it will be A transpose because this one comes first, and transpose. And then this one, follows, and apply this transpose operator like this, and thus it's A transpose, which is the same as this guy. And so that way we can easily prove that this is a symmetric. Okay. And then this spectral theorem is saying that, or in general, it is always true that symmetric matrix, also symmetric matrix is by definition, or it is automatically the square matrix. So it can never be symmetric if it is a square rectangular matrix, right? The shape, even the shape doesn't match, right? To make this equation true. Okay, so if we are given a symmetric matrix, and then the spectral theorem is saying that this symmetric matrix will always have eigen decomposition. Okay, eigen decomposition. And why is it so? What's the meaning of it? So eigen decomposition, or what's the necessary condition of having eigen decomposition? We need to have n linearly independent vectors, and also that means, even though I didn't discuss it in detail, but the necessary condition for that is the determinant of A minus lambda I equals 0. So that need to have n real number of root. Okay, n number of real root, right? The solution for this nth order polynomial of this determinant of A minus lambda I equals 0. Okay, once we found the solution and list of all of them, and then all the solutions should be real. Okay, otherwise, it is also related to this algebraic multiplicity and the geometric multiplicity. But once we cannot find the n real solutions of our polynomial equation, the polynomial equations, and then once we found n real numbers, and then that will give us n linearly independent eigenvectors. Okay. Let me mention one additional thing to make it a little bit more comprehensive, although it's still not perfect. But suppose we obtain this 3 by 3 matrix A, and the lambda times I, and determinant of it being 0. And this is, this equation has its own name. So what is the name of this equation? So this is, of course, a third order polynomial. But this equation is called characteristic equation. Characteristic equation of matrix A. Okay, and in Korean, 이거를 그러니까 특성 방정식이라고 불러요. 그러니까 어떤 매트릭스에 뭔가 특성을 규정짓는 방정식이다 이거예요. 그리고 그 특성이 뭐냐? 결국은 아이겐밸류와 아이겐벡터를 알고 나면 그 매트릭스를 우리는 그 매트릭스의 특성을 싹 다 파헤친 게 되고요. 싹 다 파헤쳤다는 그 특성이 뭐냐? 아까 얘기했던 그 매트릭스, 그러니까 매트릭스의 비밀이라는, 비밀이라고 거창하게 이야기를 해야 될지 모르지만 지금 그 매트릭스가 가지는 그 어떤 고유한 어떤 그 주된 특성이라고 하는 거는 아까 얘기했던 것처럼 아이겐 벡터들로 다 분해를 하고 나면 결국은 그 매트릭스의 곱은 이 아이겐 벡터들에 대해서는 다 스케일러 멀티플이다. 이거. 네. 요게 실제로 그 매트릭스가 가지는 어떤 네, 주된 특성이라고 우리가 정의를 하는 거예요. 그래서 이거를 이제 캐릭터리스틱 이퀘이션이라고 부르고 직관적으로 해도 그렇고요. Okay, so in this case, it will be third order polynomial, and then suppose we found the lambda as 1 and -2 and 5, which are all real numbers. Okay, all real numbers. And then we plug this guy over here, and over here, and then we will still need to find the solution for this guy being equal to 0, 0, 0, right? Yeah. So we need to find the non-zero vector over here, and then it will give us our eigenvector corresponding to this guy, and then it will give us the eigenvector of this guy and this guy, right? And there is a theorem, and yeah, I strongly encourage you to check out the proof about it, which is a really yeah, not difficult one, but yeah, once the eigenvalues are different, yeah. So yeah, how can we guarantee that these three eigenvectors obtained from different eigenvalues are linearly independent? Okay, so this guy will give us its own eigenvector, and this guy will give also its own eigenvector, but they may or may not be linearly independent, right? But there is one theorem saying that if those any two eigenvectors are from different eigenvalue, okay, and then they are guaranteed to be linearly independent. Okay. That is one kind of theorem that we can easily prove. Okay, so in this case, once we have three real and three independent, three different numbers as our root or solution of this characteristic equation, and then even before we actually obtain those eigenvectors, it's time to guarantee that we obtain three linearly independent eigenvectors, and thus the eigendecomposition exists. Okay? But what if we have the root of this eigendecomposition as all real values, but what if we have this same eigenvalues, like twice? So in this case, our characteristic polynomial would be something like this: 1 minus lambda and minus 2 minus lambda squared is equal to 0. Okay, so in that case, it will give us two real solutions of 1 and -2, but just considering their count, which is found over here, so we can just repeat it that many times, right? So in that case, when computing their eigenvectors, we can use this eigenvalue to obtain its own eigenvector, and we can use this value to obtain its own eigenvectors. But in this case, there is a two possibility. The first possibility is that this guy gives us only one eigenvector, or this guy can give us at most like two different or two linearly independent eigenvectors. Okay, so we still need to check whether the actually computed eigenvectors, and from this this root that is called the algebraic multiplicity corresponding to this number. Okay. 이게 그러니까 알제브레이크는 이게 수식에서 이게 식에서 나온다는 뜻이고요. 그 다음에 이제 멀티플리시티는 이게 중근에서의 중복의 개수고요. 그래서 중복이 두 개잖아요 지금. 근데 우리는 하여튼 아이겐 벡터를 구할 때는 각각의 아이겐 밸류에서 이제 해당하는 아이겐 벡터를 구하는데 어쨌건 이게 중근이라 하더라도 뭐 같은 값으로 넣으면 뭐 식은 a-λi 그 하면 똑같이 나오잖아요. 제가 그때 a-λi 곱하기 x equals 0라는 그 이제 뭐 bx equals 0라는 그 매트릭스 이퀘이션의 솔루션이 그 벡터 x가 가지는 게 하나가 나올 수 있고 이제 두 개가 나올 수도 있어요. 그리고 그 두 개라는 게 두 개의 이제 리니얼 인디펜던트 한 그게 나올 수도 있고 하나가 나올 수도 있다는 거예요. 네, 그리고 저게 좀 약간 좀 널 스페이스랑 좀 관련이 있고 이제 매트릭스의 랭크랑도 좀 또 관련이 있는데 이제 그게 이제 어떤 거냐면 영어가 이렇게 날이 가면 갈수록 힘들어져갖고 미치겠네. 뭔가 이거 강의하느라고 머리도 돌려야 되는데 이게 트랜슬레이터도 또 한쪽에서 열심히 돌려야 되고. Okay, so let's look at this example. So given this matrix A, so all the possible solution of this matrix, this equation is called the null space, and yeah. So what's the condition that this vector need to satisfy? So if we apply the inner product perspective of matrix multiplication, and then it should be, I mean, this inner product should produce 0, and this inner product should also 0, right? Should have 0, right? And then let's think of the direction of 1, 2, 3, and oops, -2, -4, -6, and 3, 6, 9. So they are pointing to all the same directions, right? The same direction. And then let's try to find all the possible vector x that are orthogonal to this single vector direction, right? So that will be our solution because once we found the orthogonal vector to this, and then that will be just satisfy that because the inner product with them will be all 0. So yeah, for this given vector, and then we found one orthogonal vector, right? And then another orthogonal vector, right? Which is, so the second one, this is which is still orthogonal to the given vector 1, 2, 3, right? This guy is linearly independent of the previously found solution, right? So that way, if that is our a minus lambda I when lambda was -2, for example, in that case, it will give us two linearly independent eigenvectors, right? But how many eigenvectors can it give? Okay, so that upper limit or the maximum number of eigenvectors that a particular eigenvalue gives is limited by that algebraic multiplicity. Okay, so again, so this -2 has the algebraic multiplicity of 2, and then it will give at most or maximally, like a maximum possible linearly independent eigenvector that this root can give us will be 2, but it could be 1. Okay, so it turns out to give us just only one linearly independent vectors, and then we just end up with only two linearly independent eigenvectors, and thus, yeah, it's just ending up having no eigen decomposition. Okay, so in conclusion, we obtain the solution, and then there we consider or count their algebraic multiplicity, and this guy is what is the algebraic multiplicity? It is 1 because we have 1 over here as a power, right? Its algebraic multiplicity is 1 and 1 and 2, right? And then it will give us at least, I mean, for each of these values will give us at least one eigenvectors, because that's how we computed these two values, by making a minus lambda I singular or linearly dependent column, right? In a minus lambda I. So we should be able to find at least one non-zero eigenvectors. Okay, and then again I mentioned that if these two eigenvalues are different and their corresponding eigenvectors are always linearly independent. Okay, so we don't need to worry about the redundancy or linear dependency between the eigenvectors coming from different eigenvalues, right? Okay, but still in this case, what is the total sum of algebraic multiplicity? It will be always n, because it's a third order polynomial given the 3 by 3 matrix, and thus the maximum, the sum of the total algebraic multiplicity will be 3, right? And so it will, each root will have 1 and 2, okay, whose sum is 3. But in case algebraic multiplicity is more than or equal to 2, in that case, there is a possibility that that guy gives us only one or strictly less number of linearly independent eigenvectors than its algebraic multiplicity. Okay. Okay, and so yeah, back to this symmetric matrix case. Okay, symmetric matrix case. It is guaranteed to give us all the real eigenvalues, and that real eigenvalues will give us eigenvectors that has the maximum possible numbers. Okay. So there is no cases like, okay, so this guy has a algebraic multiplicity has 3, and then it only gives us maybe 1 or 2 linearly independent eigenvectors. That's not going to happen in the case of symmetric matrix. Okay. Yeah, we can also prove that as well. Okay, and also, yeah, so that way symmetric matrix is guaranteed to have eigen decomposition, and also their eigenvectors are orthogonal to each other. Okay, so yeah, I don't have the time to prove, but yeah, I also encourage you to just to look for some proof. And in general, you can study on your own about this symmetric eigen decomposition or this spectral theorem. So that is a really kind of core part in the linear algebra. So okay, and then yeah, we need to discuss about this, right? Yeah, even though I have some more things to discuss about singular value decomposition, but we kind of promised that we will understand this, right? In terms of the number of an eigenvector or eigenvalue or yeah. Okay, so in this case, let's look at this matrix A and its induced matrix norm. Okay, L2 induced matrix norm. So in this case, what is an L2 induced matrix norm? So when applying L2 norm, so you guys remember that this guy is the definition, right? And so in this case, yeah, let's look at just a special case where A is 2 by 2. Okay, A can of course be rectangular matrix. Okay, so it can be extended to rectangular matrix, and in that case, we need to just involve, or we need to consider it's a singular value decomposition form instead of an eigen decomposition. But let's just think of A is just a square matrix 2 by 2, and also let's make an additional assumption that this matrix is has eigen decomposition, which means they have two linearly independent eigenvectors. Okay. Okay, and then so we have a freedom to choose any vector that has the length of 1 as an input vector, right? And then now let's think of it's a decomposition in terms of our eigenvectors. Okay, so suppose we have some particular eigenvector over here and maybe over here. And then in order to represent this given vector, and then we need to make this a parallelogram, and the scalar multiple between this vector and that vector will be the first linear combination coefficient, and the ratio between this and this will be the linear combination coefficient, right? So that way, the summation of these two vectors will produce this guy, right? And then, yeah, we can kind of consider their matrix multiplication with the A, right? Okay, so if our eigenvectors, two eigenvectors, so these two eigenvectors are actually, we just make their lengths equal to 1, okay? And then suppose this guy has the eigenvalue of 3 and this guy is 2, okay? So in that case, if we have this matrix, okay, let me finish it within maybe 2 minutes. So suppose this is our two eigenvectors, okay? And then let's make also assumption that those two also have a unit norm, okay? And then we can imagine this a circle, and then from here, we have a freedom to choose any vector, right, as an input to obtain the maximum ratio, right, between these two. Okay, and then this guy can be represented as a linear combination of these two, but in this case, the corresponding parallelogram will be like this, right? And then suppose the eigenvalue corresponding to this guy was 3 and this guy is 2. And then this vector will be multiplied by 3 because when multiplied with the A, right? And then this guy having the multiplication with the 2, right? And then the resulting vector will be this, right? And then how can we maximize the vector length, okay, in terms of this, in this perspective? So any arbitrary vector will be decomposed into two, right? And they have their own corresponding linear combination coefficients, and then those two values will be multiplied with its own eigenvalues of 3 and 2, and then they will be merged or combined together, right? And then in order to maximize the length of the resulting vector, we can just assign the linear combination coefficient all the way to this guy, because this guy will be multiplied further, right? So the best strategy to maximize the resulting vector length is to just align this guy with the first eigenvector, right? And that way, the maximum possible value of this linear combination coefficient of 1, for example, okay, so that will be multiplied with the maximum possible eigenvalue of 3, and then the vector length will be 3, right? But if it is like this vector which has the linear combination of these two, but in that case, necessarily the linear combination coefficient will be strictly less than 1, right? Because for example, in this vector, it will be forming like this parallelogram, and thus the vector length has reduced, and thus the scalar multiple or coefficient is strictly less than 1, right? So we have these two strictly less than 1 kind of a linear combination coefficient, and then they will be multiplied by 3 and 2, and they will be merged back. Okay? But so we don't give we are not showing the rigorous, we are not doing the rigorous proof, but intuitively, we can align this input vector exactly on the vector that has the largest eigenvalue. So that's how, that's the best strategy to maximize the length. And then what is the corresponding ratio between the two vector lengths of the input and output. It will be simply largest eigenvalue, right? So that way, if it is a square matrix and also has a eigen decomposition or n linearly independent eigenvectors, and then this guy is singular value, maximum singular value, or if it is a square matrix, and then the maximum eigenvalue will be our norm of this matrix induced matrix norm. Okay, so yeah, that's it for today. Okay, and then in the next Wednesday, we will have an exam starting at 10:30 as announced. Okay, please do your best to prepare for exam, and then good luck on your exam. Thanks.